Greetings of the day and welcome to this session. This session is divided in two parts. In the first part, we are going to look at the power of geophysics for dam investigations, including leak path detection, finding out abnormal zones within the dam body, including low density zones, etc. And the second part, we are going to look at application of geophysics throughout the life cycle of tunneling. So I'll start sharing my screen now. So we'll start with the first part of this, which is harnessing the power of geophysics for dam health assessment and dam monitoring. A very, very brief introduction about myself. I am Sanjay Rana. I'm a professional geophysicist having 35 years of work experience. Presently, I'm managing director of Parson, which is an engineering geophysics company, and also chairman of AF Academy, which is involved in offering various educational courses in the field of geophysics. I graduated in 1990 from University of Roorkee, which is IIT Roorkee, post which I worked briefly with state government, that is UP state government, where I was mostly involved in well logging operations, and then Department of Atomic Energy, Atomic Minerals Directorate. In 1995, I turned an entrepreneur, starting the first ever engineering geophysics company in the country. So that's the time I pioneered this use of near surface geophysics in private sector in India. Till now, I have completed geophysical investigations of more than 2,000 projects. And I'm also involved in development of codes and practices and standards with various bodies like BIS, IRC, TAI, INDSTT. I'm the principal author of a few guidelines, like the one on geophysical investigation of dams, geophysical investigation of tunnels, geophysical investigation for bridges, which is IRC guideline, and Indian Code for Subsurface Utility Mapping. So with this brief introduction, let's go to our topic of the day, which is geophysical investigation. So for the uninitiated, I always like to introduce geophysical investigation with this particular picture, because this is something which all of us understand very well. Here we see MRI images, X-ray images, CT scan images. So these are basically medical images. What are we doing here? We are sending different kind of rays and waves inside the earth, inside the human body, I'm sorry, to create a picture of what's inside the human body, right? It can be a fracture, it can be some tissue damage or whatever. So depending on the objective, we are sending different kind of rays and waves. That sometimes we are using X-rays, sometimes we are using magnetic resonance imaging, sometimes we are doing computer-aided tomography, etc., or ultrasonic waves, for example. So that's how we are doing it. Now, if you compare this to the images here, which are basically geophysical images, right? So in geophysics also, we are sending different kind of rays and waves inside the earth or the structure to create an internal image of the particular structure. Now, these can be seismic waves, these can be electrical fields, or we can be measuring naturally occurring fields, for example, gravitational field or magnetic field, etc. So here, for example, you see a concrete dam, which has been investigated using a seismic tomography between the downstream and upstream phase, and we can see the fracture zones very clearly. Similarly, a masonry zone in masonry dam investigated, etc. I'll go in detail of all this. Idea of these two slides was just to tell you that we can understand geophysics to a large extent like medical imaging. That is, without cutting open the body, without doing any drilling, we are trying to see what's inside a structure or what's inside the earth. Now, when it comes to geophysics for any application, but most importantly, here we are discussing about dams. First question is, which technique or tool should be used? That is a very, very important choice, that which particular tool we are using for what application. For that, we need to first of all define the objective, whether we are looking at seepage or leakage paths, whether there is a subsidence which has been observed in the dam body and we want to investigate that further, whether we are looking at the strength of the dam body after, let's say, it's 50 years old or 100 years old, and we want to understand like what is the remaining strength in the dam, residual density. Let's say there has been seepage which has been taken place through a dam for a long time. Of course, there some leaching must have happened. So what is the residual density now? So that objective has to be defined very clearly, and based on that, we have to choose the right tool. Second is consider depth of investigation required. Dams can have different heights. Any dam more than 15 meters is, for example, categorized as a large dam. So a dam can be 15 meters, 30 meters, 50 meters, 100 meters, 130 meters. So depending on the depth of investigation, again, we have to choose which tool has to be used. Then consider dam height to length ratio and geometry of dam. This is another very important parameter to be considered because there are certain methods. For example, we talk about electrical resistivity imaging. As we go in detail of the method, you will understand that in electrical resistivity imaging, the depth of investigation is, let's say, 1/5 or 1/6 of the total spread length which you are able to put. So depending on the dam height to length ratio and the geometry of the dam, we have to decide which method is best to be used there. And always remember that wrong choice of tool can result in complete failure of geophysical program. Now that's one mistake we should never make, because if we are choosing a wrong tool for a wrong application, ultimately we will not get the results which we desire. And that will result in complete failure of geophysical program. And the end user who is not so aware of geophysics or geophysical methods will ultimately get an impression that geophysics did not work here. It was actually the wrong tool selection which was responsible for the failure. So as practitioners, it is our responsibility to make sure that we choose the right tool. When it comes to tools, there are a number of tools which are available. For example, I have listed few tools here like electrical resistivity, streaming potential, seismic tomography, seismic refraction, GPR, MASW, refraction, microtremor. And here we have listed issues and concerns of dams and appurtenant structures. For example, in concrete dams, you can have things like cracks, be it on dam top and galleries. You can have degradation or density loss. You can have water leaks. Similarly, in masonry dams, we can have degradation, density loss, water leaks. In earthen dams, we can have leak path detection, internal erosion, strength issues, subsidence issues, cavities, sinkhole. Other than the dams, then we can have issues with stilling basin and we need to find out their condition for erosion, for damage. Then we can have issues with the canal leakages. And sometimes the problems are there in the foundation of the dam, not in the dam body itself. So that's what we call foundation defect. And if you see, there is one or the other method which comes as most suitable or moderately suitable or not suitable. So for any of the problems, like I'm not going through this table as such one by one, but for any of the problems which can be listed in terms of a problem with a particular kind of dam, there is one or the other method which is available to solve that problem. So now we'll start with few problems and try to see how different methods are contributing to their solution. So for example, the first thing we are going to talk about is concrete dam. And let's say degradation and density loss. This is the problem we are looking at. And the method we are going to talk about is seismic tomography. We'll practically talk about all these methods one by one. First, we are talking of seismic tomography. So when we talk about tomography, the word tomography itself comes from tomo plus graphy. Tomo is a slice and graphy is to write. So to write a slice is where the tomography comes from. It's an image which it's a term which is used a lot in medical imaging. We have this CT scan. So there, if you have seen that they give slices of different parts of your investigated area. Similarly, in geophysics also, we are doing the investigation and practically creating the slices of the subsurface to be able to visualize the physical properties there. So when we talk of seismic tomography, the word seismic is coming because we are using a source which is creating these elastic waves. All right. So these seismic waves are propagating through the structure, and ultimately they are being received. And through the process of interpretation, we are finding out where are the weak zones inside the body of the dam. Now here we have two different type of tomography approaches. One is called L-section tomography. So as the name indicates, this basically covers the entire dam body. So let's say this is the gallery of the dam, and this is the top of the dam. And here is the spillway, and this is the top of the spillway. So we put our transmitters or the short points on the top of the dam and on the top of the spillway, and our receivers will go in the gallery. So this is what transmitter short points on the dam top and spillway crest. And here you can see a person is marking the short points where we are going to start the wave propagation. This wave, of course, is we are not using any explosive in a sensitive structure like dam. We are going to use a hammer. It can be a 5 kg hammer or 10 kg hammer, depending on what is the total height which needs to be covered, so that our waves are strong enough to be captured on the other side and we are able to pick the first arrivals properly. So here is a person ready for hammering on the dam top. Once we go to the spillway, of course, you need to go on the spillway crest. And again, you can see these people standing there. Of course, they use all the safety harnesses and all safety protocols are followed. And they are ready to strike on the dam, on the spillway crest. And the receiver points are in the dam gallery crown. So this is the dam gallery, and here in the crown we put our receiver points, something like this. So you can see here drilling has been done, a small drill has been done, and receivers have been put in the crown of the gallery. So now what we are going to do is we are going to initiate our elastic waves from here, and we are going to pick these waves in the gallery. Ultimately, when we do this entire exercise, idea is to make a dense crisscross of the ray paths. So here are these ray paths. For example, these gallery generally has 24 or 48 receivers at one point. So once one shot is initiated at one point, it is received by these 24 or 48 receivers in the gallery. Then we move to the next point and the next point, and the same sequence continues from one end of the dam to the other. This is an example of a dam which was around 470 meters. And as you can see, there's a huge crisscross of ray path which has been created here. Now, once this data has been obtained, of course, you pick up the data, calculate the arrival times, and then go for the inversion. And after that, you have this p-wave velocity model, which very clearly shows you the p-wave distribution inside the dam body. So for example, it is from 3,100 to some 5,700 meter per second p-wave velocity. And we generally look for the relative changes because it's impossible to actually say that every dam will have this kind of p-wave velocity. That's not true, because every dam has a different construction history. It has been constructed using different kind of material. Even the masonry used can be very different. This was a masonry dam for that matter. So we do not have an absolute value of velocity attributed to one particular type of dam. But what we look for is the relative changes. Because see, if you look at this dam, most of the dam body is having velocity which are exceeding 4,400 meter per second. But then there are certain zones, for example, a zone here, for example, the zone here, for example, zone with little less velocity, but this one is most profound, this one is most profound, and this one is most profound. And of course, this one. So like this, we look for the relative changes in velocity to see what is the reduction in velocity in which parts of the dam. So this gives you a view in L section. Like, for example, it is like cutting a slice from the dam top up to the gallery and taking this slice out to give a feel of what is the internal condition in terms of p-wave velocity distribution. If a dam is having multiple galleries, for example, this is an example of a dam where it has 1, 2, 3, 4 galleries in this dam. This is a pretty high dam. As you can see, 840 to 710, so it's around 130 meters total elevation. And you can do the same thing between, let's say, dam top and first gallery, this is the spillway, so spillway crest, again spillway, so spillway crest. Then from the first gallery to the second gallery to the third gallery, and third gallery to the last gallery. So same procedure can be adopted even if there are multiple galleries. And at the end of it, you have a complete picture of the P-wave velocity distribution in the dam body, where you are able to pick up very clearly what are the low velocity zones, where are these zones located, and this gives in the complete glimpse of your dam body. So this is what we call L-section tomography. Now, once the L-section tomography has been done, next question is that what is the condition of dam from upstream to downstream? For example, this has given you one slice from the dam top. But then the next question is that my dam has a certain thickness also. I have upstream, I have downstream, and the dam is having certain thickness. How do I know what is the condition from upstream to downstream? For example, if we want to see a deteriorated zone, how much is it going from upstream to downstream? That's also important critical information. For that, what we do is, once we have done the L section, then we choose the location where some weakness has been observed. Let's say some weakness has been observed here. And then we choose this location for doing a cross-section tomography. So in cross-section tomography, again, we are having the upstream phase and the downstream phase. Same thing, we will have receivers on the upstream. In the area where there is no water, you can use normal, accelerometers or geophones. Where there is water, you can use hydrophones. So there is no need to empty the reservoir to do this study. And in this particular phase, we can use again hammer for the source. There is another approach which is possible. That is, we use downstream to as the receiver, and in the upstream we are using hammer on the waterborne area and sparker in the hammer in the dry area and sparker in the area with water. So mix approach is possible in this. And once again you process this data, what you get is extent of your weak zone right from upstream to downstream. So in L section, you had seen the extent of the zone in this direction, that is along the axis of the dam. And now in cross section, you have seen extent of this zone across the axis of the dam. So you practically have a three-dimensional view of your dam body. So this is the strength of combining L section and cross section tomography. Then what we get is, of course, P-wave velocity. Engineers are sometimes interested in density rather than just P-wave velocity to understand it better. So using Gardner equation, we can change this P-wave velocity to density. And you can see this is the velocity tomography, and now you have the density tomography. And here you can see very clearly that what is the kind of change in density. For example, in good area, if the density was, let's say, 2.6, and in the bad areas, it has come to 2.2. So that has been the reduction in the density over a period of time because of leaching. So now you know the affected area, you know how much density deficit has taken place, and based on that, you can plan your entire rehabilitation. So this is about seismic tomography, a very, very strong technique. The next issue and concern I'm going to quickly talk about is water leaks. Okay, water leaks can be through masonry dam, they can be through earthen dam. And here we are going to talk about first the electrical resistivity method, which is one of the strongest method when we are talking of anything which changes the resistivity or conductivity of the subsurface. So here we are going to talk about electrical resistivity imaging. It is working on the principle of one of the oldest geophysical methods, is electrical resistivity method. That is, if there is a current passing through a medium, potential is developed, and then by the Ohm's law, V is equal to IR. Once you know the voltage, once you know the current, you can calculate the resistance. Resistance multiplied by geometric factor, you can calculate the resistivity. That is the basic fundamental of electrical resistivity method. Here, what is different in electrical resistivity imaging is that rather than using just 4 electrodes, we are using multiple electrodes, and we are doing profiling and sounding at the same time. So in a way, you are getting a 2D or 3D section of the subsurface. So this is how your line is laid out on the dam. So your electrodes are put at a particular spacing all along the dam crest. Here is a person standing, taking the going ready to take the readings. And once you take this data and you process this data, just like in the earlier L section of seismic tomography, you are having a P wave velocity distribution. In electrical resistivity imaging, you have your resistivity distribution. So, for example, this is the dam which has been investigated. All the good areas of the dam have the resistivity which are in almost in the reddish font, and whatever areas have got more saturation of water or concentration of moisture, they have come as low resistivity areas. So as you can see, this dam is almost 450 meters, and you can very clearly see that just by doing this electrical resistivity imaging, you are able to find out which are the zones where there is more moisture content or water content. So this is again a very strong technique to find out about internal condition in terms of water content. And then once we have found the water, there is more moisture content or water content in certain parts, the next point is that whether there is a water flow taking place through this, that's where streaming potential becomes very important. So in streaming potential, what we are doing is that we are measuring this naturally occurring potential, which is being developed because of flow of fluid through porous medium. So when the fluid is flowing through the porous medium, the positive ions which are attached to the clay membranes are being displaced. And because of that, a potential is developed. So let's say we are having this dam. This is the crest of the dam. This is the reservoir. So we can do one line in the reservoir, one line on the crest, and then one line in the, or one or two lines on the dam face, wherever we have things like berm. Wherever the water entry is taking place, we have a profound negative SP development taking place. And similarly, whatever lines we are doing after that, we'll have this SP development. And at the exit point, which can be pretty far off from the dam also, you'll have a positive SP development. So ultimately, you get a clear idea of your seepage path. So this is how SP is used very effectively to give you seepage path through the dam. And once we put because SP is interpreted in qualitative terms, not in quantitative terms. That is, SP gives you that there is some movement or some flow which is taking place at this particular location, this particular chainage of the dam. Now, to understand what is the depth of this zone, what is the total extent of this zone, we go back to our electrical resistivity imaging results. For example, in this particular dam, you can see there is one low resistivity zone here, one low resistivity zone here, and one low resistivity zone here. Once the SP has been conducted, it becomes very clear that maximum SP development is taking place through this particular zone, across this particular zone, which means that although all the three zones are having a higher level of water or moisture concentration, at the moment, the maximum flow is, or all the flow is taking place across this zone only. So it helps you understand your seepage paths much better. And ultimately, once you have done your ERI and SP, and you put the results together, you can actually map your seepage zone from one end to the other. And then based on that, the complete rehabilitation of dam can be taken care of. Then we are also going to talk, so we have talked about electrical resistivity, streaming potential, seismic tomography. Now I'll try to talk very briefly on the stream basin condition or erosion damage. So sometime in stream basin, there has been, let's say there is an incidence of flood where some boulders have come and you suspect that there might have been some damages in the stream basin, and we want to inspect it. If we empty the entire stream basin for inspection, obviously it means that we have, it affects the operation of the dam. So that's really not required. Using the tools of GPR, we can do the investigation from, even if the water is there, and based on this investigation, we can make the complete map of the stream basin deterioration, for example, which has been done in this particular case. And best is that this was done somewhere in Bhutan. And after 2 years, once the stream basin was emptied for inspection, the results which were derived from GPR matched wonderfully with the actual site condition there. So this is the application of GPR for inspecting your stream basin. Then we'll talk about foundation defects. This also is a very important topic. As I said, sometimes the problem is not through the dam body, but through the foundation. And there, various tools are of importance. Electrical resistivity imaging, which we discussed earlier, is very important for that. It can be used to see the foundation defect. The only thing is that your depth of investigation has to be good enough that it goes up to the foundation. Second method, which can be used very effectively, is seismic refraction. So in seismic refraction, again, we are sending the seismic waves from the top, receiving it from geophones all along the dam body. And then this is seismic refraction tomography. Then we are creating a P-wave velocity distribution of the subsurface. Seismic tomography and seismic refraction are very different, because in seismic tomography, we are talking of direct arrivals. Here we are talking of refracted arrivals. And once we do that, so this is a particular dam which was investigated. You can see this is the foundation. And here, this particular zone shows a particular weakness in the foundation. Similarly, in this example, you can see how the foundation is going down in this particular area. So for foundation defect, you can use very effectively combination of electrical resistivity imaging and seismic refraction, and even MASW if it is possible to go up to that depth. Seismic refraction is also used for phreatic surface mapping, because we know that when the phreatic surface is encountered, your velocity will change and definitely exceed 1400 to 1450 meter per second. And based on that, the phreatic surface can be mapped using seismic refraction. So this is one good example of phreatic surface mapping. Another important tool is MASW, or refraction microtremor, both of which are giving us shear wave velocity information. You see, if we have both P wave velocity and shear wave velocity, we can actually calculate all the dynamic modeling. We can calculate Young's modulus, shear modulus, bulk modulus, Poisson's ratio. And that is why when we are looking at subsidence studies or degradation, MASW and REMI also become very important. They are based on dispersion properties of Rayleigh waves. So we create the Rayleigh wave dispersion curve. Equipment more or less remains the same as seismic equipment, which we discussed earlier, except that your geophones are generally 4.5 hertz in this particular case. And once you process the data, so this is the dam top. As you can see, this is the depth. This is the bedrock level and foundation level, you can say. And this is the result of refraction microtremor. So it's around 100 meters depth. And it's very, very clear that this is the dam velocity, shear wave velocity. And in this particular area, the velocity is much lesser. This particular block, the velocity is much lesser. So because of lot of seepage of water over a period of time, a lot of leaching has taken place, and that's how this block has become very, very weak. So this is another very important method for dam investigations. Then we have canal leakage issues. Sometimes there are a lot of leakages which are happening from the canals, and we are not able to, we don't know where this leakage is coming from. We just observe it because of something coming in the downstream field, or some water level rise there. But we need to understand where exactly this leakage is coming from so that we can repair it. And for that, again, the combination of electrical resistivity imaging and streaming potential come in very handy. So this is, for example, the canal. Here we do multiple lines of ERI and SP, and we are able to see the bad zone, or the zone of low resistivity, which means there is more water concentration there, and corresponding SP development, which gives a very good information about the seepage path. And once you do multiple lines, you can actually draw the path of seepage in the canal also. The next question is, when do you need to investigate your dam? So the fact is that it is desirable to have a baseline data of dam soon after completion of the dam. So because just like when we turn 40, doctor generally advises us to go for a ECG. And he says that this will work as your baseline ECG, and in future we can always keep comparing with this. Similarly, if you create a structure, you make a structure, it's always good to have a baseline data on the structure. So ideally, every dam which is being constructed, soon after completion, it should be done. But fact is that there are dams which are more than 100 years old, and at that time, these techniques were not even available. So for older dams, this time is now. So once these techniques are available, they should be investigated now. Of course, if you are doing a rehabilitation planning of a dam, you need to know exactly where you have to do your intervention. So, for example, if you are going for surgery, you always have the background information like X-ray or MRI images for doctor to guide exactly where the surgery is to be performed. So, similarly, unless you have this inner insight of the dam body, rehabilitation plan cannot be properly made. And then once you have done a rehabilitation, you have to check efficacy of the rehabilitation, whether it has served the purpose, whether it has actually eliminated the problem for which it was attempted. So after carrying out rehabilitation, changes in physical properties are much easier to interpret than one-time measurement values. So it's always good to repeat these measurements at a particular duration. They can be every couple of years or 5 years. That is depending on of course, the criticality of the dam, the importance of the dam. But ideally, we should keep repeating these measurements, because once we see change from, let's say, year 1 to year 1+5, we will know how the dam is deteriorating in this particular period. So ultimately, the conclusions of this small session, that geophysical investigations must be made an integral component of dam safety inspection program and procedures. Periodic inspection must be carried out on all large dams to detect problems at early stages. Geophysical investigations must be carried out before designing the rehabilitation program and after rehabilitation. These methods has great potential for other applications like canal seepage studies, stain basin checks, etc., etc. And geophysics presents a viable option to conduct scientific inspection and investigation of more than 6,000 specified dams within next 5 years, as stipulated in Dam Safety Act 2021. Guideline document is already available for these investigations, which should be ideally deliberated and talked about in the community. So thank you very much for your attention. And in the next part of the presentation, I'll be talking of harnessing power of geophysics in entire life cycle of tunnels.